that being said, let's take a look at our diagram that we have here. We have some given information already. We see that we're working with a 60-volt battery, and we have information for each of our 3 resistors. So one of the things I teach my students is we should always write down the given information that we have. So we know that our total voltage is 60 volts. So we're going to put that in here, 60 volts.
Now, who's taking physics now? Oh, you'll see this. And you'll see it exactly like this. So I'm getting you ahead of the game.
And we know that our resistor 1 is 17 ohms, resistor 2 is 12 ohms, and resistor 3 is 11 ohms. And so our objective then is to solve for all of these open areas. Okay?
Shalom and welcome to Israel Institute of Biblical
Okay,
Studies.
thank you for the
Located
commercial.
not far away from.
Alright.
So with that, one of the ways that I believe...
So what's the total resistance, guys? You just add them up. Okay. Alright. 17, 12, and 11. So he's going to put 40 ohms right there. Now, using Ohm's law, can you find the current now? Well, you know the total voltage, and you know the total resistance. Okay, so it's going to be 60 divided by 40, isn't it? So the ohms is going to be, what, 1.5? Yeah. So your current is going to be 1.5, and what do we know about the current around the whole system?
Stays the same.
It's going to be 1.5 amps, okay? Now, can we go back and find out what the voltage drop is going to be across each of those resistors?
Yeah.
Work Ohm's law backwards again, okay? You know that the current is 1.5 volts, and you know the resistance is 17 amps across here. Use Ohm's law and find what the voltage drop is there. Boom. Do it again. Okay, let's try it. He'll show you how to do it.
Is the best way to go about starting these problems is you always want to try and solve for the totals first, like total resistance and total current or total voltage. Try and get those first, and then everything else will kind of come after that. Okay, so one of the things that we can solve for is we can solve for our total resistance, because all we have to do is add up our 3 resistors and we have that information. So to get this total resistance right here, we're just going to add our 17 ohms plus our 12 ohms and our 11 ohms. And when we do that, we get a total of 40 ohms. Okay? So we can fill in that blank. And as I mentioned, as we solve for each of these totals, we're going to come back to this equation right here. So as you see, I've got my total resistance and I've got my total voltage. So my missing unknown, or my unknown value for the total, is the total current. Well, let's just go ahead and plug that in to V equals IR, and we can then solve for our total current. So our voltage here is 60 volts. That's going to equal our current times our resistance, which is 40 ohms. So to get I by itself, we're going to divide by 40 on both sides. When we do this, our total current is going to equal 1.5 amps. This is valuable information. We can plug that in right here, 1.5 amps. Now that we know the total current, let's go back to our rule, which states that the current at every single place is the same. So if my total current is 1.5, well, my current at the first resistor also has to be 1.5. So we can fill in all of these because the current is the same at every single position. Okay. Now all we're left is to solve for each of these velocity drops, okay, which basically is
Voltage drops, so I'll take that. He's a physics kind of guy. He gets his velocity and voltage mixed up. So what do I do with these? R times I, R times I, R times I. Right? How easy is that? Okay? And then when I get these totals here, they better add up to 60 volts. Okay? So why don't you guys figure that out? 17 times 1.5 is what?
25.5.
Say again?
25.5.
Okay, so you're telling me the voltage drop across here is 25.5?
Right.
Okay, volts. So 60 minus 25.5 leaves you about 34.5 volts to drop across the other two.
Next one's 18,
Okay?
next one's 16.5.
18 and 16.5. You add them up, and sure enough, it ends up as 60 volts, doesn't it? Okay? And that's basically how you do, and I'll let him
Telling us,
finish up.
not velocity
Pretty
drops,
much.
our voltage drops, which
Very
is
big
telling
deal.
us how many volts are being used as the electricity flows through all of these resistors. Okay? And the way that we do this, just like how when we use our Ohm's law for the total resistance, total current, and total voltage, at the first resistor, we're going to have to do that the same. We have to, for V equals IR, we have to do the resistor 1 and current 1 to get voltage 1. To do it for the second one, we have to do all of the second resistor, all of the third resistor. So we can't intermingle our resistors and our total values. Okay? So to find this first voltage drop, we're going to be using our 17 ohms and our 1.5 amps. And with our equation, it's very simple. We're just going to multiply these two because it's going to be our current times resistance. Okay? And so to show you this, so V1 is going to equal our 1.5 amps times our 17 ohms. And that's going to give us a total voltage of 25.5 volts. Now for our second voltage drop, it's still the same, 1.5 amp.
All right, I don't think I need to go through the rest of that. I think he's figured that out. Now, what do I want you to know about series circuits? Here we go, take some notes. Okay, number one path. Okay, so number two, if that path is open, what happens to the current through any load that might be on that thing? Okay, one path, if you open the circuit, it must be closed to, for the electrons to flow, right? So if anything, like if you had two light bulbs in series, if these three were light bulbs, if one of them went out, like your Christmas tree lights, they all go out, right? So you can tell Christmas tree lights which ones are wired in parallel and which ones are in series, because if they're series, then if one goes out, everybody in that string goes out. Why? Because there's only one path. Okay, so you're opening the circuit. Okay? So that's the next thing I want you to do. Third thing I want you to know is that the total resistance, okay, in a series circuit is simply the sum of the resistances. So however many resistances you have on that series circuit, add them up. You can write it down this way if you want to, that's fine. If you want to be really a math genius like me, not. All right, you would go the sum of the resistances, or RT, the total, equals the sum of the resistances. Ooh, look at that. You almost think I know what I'm doing. Okay, that's what that means. All right, however many resistances you have on that series circuit, all right, you just add them up. That's what that means. Okay? And what's next is the voltage. What happens to the voltage across each of the resistances? The total voltage is the sum again means is you get a voltage drop across each load in a series circuit. Okay? Well, what do we know about the current? All the way around.
Stays the same.
Stay same. That's everything you need to know about a series circuit. So I total equals I1 or IN all the way down. Okay? Now a parallel circuit is just the opposite in a couple of ways. Okay? So I don't want to go there yet. Yeah, I think I'll do parallel circuits on Thursday. Alright? But I'll give you, I bet you it's not the sum of the resistances in it. Okay? I bet you these two are reversed. The voltage stays the same, and the current drops across each path. See how that works with a parallel circuit, or just opposite? Okay? And this is actually the inverse, but we'll get to that later. Okay? So the first thing I'll show you probably on Thursday, I have another video. If you want to preview that video, it's on your notes on how it's basically the same guy doing the same thing with parallel circuits. That would be cool. Okay.
Multiplied now by our 12 ohms.
Okay. So let me pull up the notes and see if there's anything else I want to hit. Okay. Yeah, chapter 2, we'll go with DC and AC. Okay, and parallel, and there's the parallel circuit. All right. And a series circuit. All right, there's your series of parallel circuits right down there. Okay, and a complex circuit just has a combination of both. These down here, this one here is series and parallel circuits, resistors and series and parallel, a little video there, I just put that one on there, that's a new one. This physics classroom stuff, that's actually some interactives. You can actually build circuits, parallel and series circuits, and then see how it works. Okay, so if you want to play with the interactives on the physics classroom, that's kind of cool. With the series and parallel circuits and a combination circuit, you can actually build your own. I think they do have an activity where you can build your own. If not, I've forgotten and I'm lying to you. Okay, let's see if there's anything else. All right, so on Thursday, we will pick it up with series circuits and DC current, direct current. And what I would like you to do is start reading chapter 2, basically, right? All right, and then next Monday, we'll meet 9:30 on Thursday, collaborate,